gentlemen. Good morning. We'll leave one of those doors open so people hear that the microphone is on and the session is beginning. Great. Okay. Welcome to the third day of this conference. I hope everybody's enjoying it. Yes. Hands up. Hands up. Yes. Thank you. Okay, so welcome to the session, dual plenary session on the battery revolution. Just give me a moment and allow me to speak as the plenary session coordinator for this wonderful conference. Did we do that? Assigned to me less than a year ago. So we gathered 40 different plenary session ideas for plenary, all of which were really interesting. 40 plenary session ideas. We then surveyed as many people as we could. We also referred to a suggestion box that USAE effectively had, and we narrowed it down to the 10 that you have now. Figured out where one goes and the other goes, and here we are Wednesday morning, just so instead. Because this, of all 40, none was more highly ranked than the batteries. I tell you this, we in particular students, want to take your raise your hand if you're a student. Why are good? Okay. So, it was also my job to pick the coordinator, so I asked Eric Pittinger, noted energy storage economist, to chair this. Eric, for reasons that are obvious, as the morning proceeds, declined and he said, go find another. So without delay, I think everybody's bio is on the website, we have a mix of policy, economics, technology, and grid science to talk about this morning. Jason Burwen with the Battery Association. I think you should just say a word about your own organization. But I'm delighted in particular to welcome Eric, and of course my own delegate in the Maryland Assembly, Marc Korman, who has led the charge, so to speak, for the worst ones. You don't even know you're saying it. Parade for battery programs in the state of Maryland, which, as many of you know, is pretty advanced. Without further delay, I think we'll take them a little bit out of order from the program. We'll start with Jason with the Energy Storage Association, followed with Eric, Professor Pittinger, and wind up with the policy thoughts from Delegate Korman. Thank you. Each speaker no more than 15 minutes. I use a timer.
That's okay. You can stop me. All right. I will be fast. Trust me, because I tend to talk pretty fast. More to the point, you all are smart enough people that there's interesting questions and discussion in the audience. So I'll just try to sort of lay out where we at the Energy Storage Association see this battery revolution, as it's being called. Again, hello, I'm Jason Burwen. I'm the Vice President of Policy for the Energy Storage Association here in Washington, D.C. We've actually been around for more than a quarter century, but it's really only in the last decade that we've turned into sort of more of a standard trade association. And we represent all parts of the value chain, so not just battery manufacturers and vendors, but the developers, the actual users of these batteries, the power producers, utilities, large end users. And of course, we are engaged here, not only here in Washington, D.C., but at each of the RTOs and in the various states. You can see some of those logos might be things you recognize. At the outset, I just want to make clear here, energy storage, the reason why this entire conversation I think is very fascinating is because it's about flexibility, supplying precisely the amount of electricity when and where you need it. And that simple decoupling of, say, the constraint that supply and demand have to meet at exactly the right level at exactly every moment gives you an enormous range of new operational possibilities on the grid. And that's why I think a lot of us are here excited about this revolution. From an industry standpoint, the value that we see in energy storage generally It's that it's really something that optimizes the use of your grid and all assets on that grid, enabling it to transform or adapt to whatever future conditions you really want to see. And the result of that is saving folks money in the form of reduced investments in excess, underutilized capacity, whether that's in the form of power plants or wires, making the grid more reliable and resilient, not just sort of balancing supply and demand moment to moment really effectively or providing on-site backup power for critical facilities, but also helping manage uncertainty and risk going forward. I think it's an understated thing, and I'm happy to talk more to. And then, of course, integrating a diverse energy mix, obviously compensating the natural variability of renewables, but also making inflexible assets capable to be operated in that system as well, and of course integrating more distributed energy resources, and of course creating a new industry here in the United States. So at ESA we talk about a lot of different kinds of storage. Sounds like today we want to really focus on battery storage, which I'm more than happy to do. The reason for the focus on battery storage is that this is the technology that has taken off across the grid recently. It's the fastest growing storage type with cost declining rapidly, and I'll get into that in a second. But a couple other reasons why this is everywhere and why everyone's talking about it. It's located on all parts of the grid. So this is co-located with generation, transmission connected, distribution connected, sited at customer facilities, in microgrids. It's actually able to be a part of every part of the grid, and that means every stakeholder in the grid also has some potential role for providing value with storage. Those systems can be deployed modularly from a tiny 5 megawatt or kilowatt project up to some of these larger power plant sized projects. 30 megawatts is the largest battery in the grid today in the United States. There's a 100 megawatt one in Australia. They're quick to deploy. Megawatt scale capacity can be deployed in less than a year. We saw deployments in Southern California after the Aliso cable failure of less than 6 months from contract approval to nearly 100 megawatts of 4-hour batteries online. That kind of just-in-time capacity just hasn't existed before. It's uniquely flexible and has expanding performance capabilities. It's instantaneously responsive and can ramp in either direction to absorb electrons or inject electrons at precisely the level you want. That's a really key thing, because that, and we can get into it a little bit later, is changing the grid from an electromechanical system to increasingly more of a pure electrical computational system. And then it's capable of multiple grid services. The storage does what its software controls tell it to do, so it can be reconfigured in real time to do many different things fairly quickly. That's the flexibility that makes battery storage, I think, really fascinating. Back to the cost piece, though, and why we're really having this conversation is this. Battery storage costs have been declining 8 to 15% year on year and are expected to continue doing so through the near future. This is being driven primarily by the electric vehicle battery market, using the same core technology of lithium-ion batteries. And so that's one thing to bear in mind here, is part of the reason these costs are dropping so precipitously is not because of their use in the grid per se, but because of the other industries that are scaling far more rapidly using the same core technology. And just for folks to be aware, in terms of, say, a 4-hour battery storage system on the grid, the batteries themselves are maybe around half the cost of the system. So this is not all battery, this is balance of systems, this is soft costs. So bear in mind that as you look forward. But this is the story. These costs are going down much faster than anyone expected, and that is why you're seeing so much more storage coming onto the system so quickly. I don't have the slide in here. I realized it as I went to sleep last night. I wanted to talk about the future of the industry, and I didn't even put my industry future slide on. But basically, we have about just over 800 megawatts of battery storage in the US grid today, representing about 1.2 gigawatt hours of stored energy capability. And that is going to be expanding, we think, to annually installations of an additional gigawatt of capacity in the 2020s each year. And you're seeing this reflected in the bids and contracts that are coming up in utility procurements. I've put some interesting notes on here. I would draw your attention to the fact that we're really talking about a scale here that people did not even think about 3 years ago when I started working with the association. PG&E has now a proposal for, not only is it 568 megawatts of 4-hour storage proposed, which would be more than the entire installed base in the United States today from a megawatt hours of capacity standpoint. But one of those projects is a 300 megawatt 4-hour battery. That is a very large facility, again, power plant size. And we've seen these kinds of procurements happening in other utilities. This isn't just a California phenomenon. I note that Colorado has now gotten approval to go forward, for example, with 225 megawatts of 4-hour batteries. And there's some bids, it's not just the procurements themselves, but also looking at these bid tables coming in from these utility procurements, I think are really fascinating because you're seeing not just interesting price points and multiple bids, but you're seeing them in interesting combinations as well. Storage alone, storage plus gas, storage plus solar, storage plus wind, and they're creating a larger and larger percent of the bids going into some of these capacity procurements. In terms of the applications on the grid, just to recognize that based on where it is, it will have different niches that it's able to provide services for. When you put it on the generator side, it's going to be doing generator services. A lot of that is going to be about peaking capacity, but also reducing curtailment, reducing generator cycling, doing the ancillary services. When you're on the infrastructure, it'll look more like an infrastructural asset, extending the life and capacity of wires. And at customer facilities, you can be doing a lot of customer end user value while also providing some of those grid services at the same time. That's a capability that, again, has drawn a lot of interest, these kinds of hybrid business models. Here's some examples. I want to draw your attention to it as a part of resource adequacy and infrastructure because that's where we see the most megawatts of batteries showing up on the grid. Note that none of these things that I'm showing you are paired with renewables. There's no particular reason it needs to be. And this is how it's showing up. I note that a lot of these are 4-hour batteries, but we're seeing now 8-hour batteries being developed. They were bid in Colorado up to 10 hours, in fact. And also another thing I want to note here is that whereas this is system capacity and therefore what we're used to, down below, network capacity, this idea of as an infrastructural asset, I think you're going to see this as a bigger growth area because a lot of the regulated entities are starting to realize that this might make sense as part of their transmission and distribution asset base. And note that on the bottom right there, that's an aggregation of behind-the-meter storage that is providing grid services in contract to the utility in Hawaii, which is, again, I think, a very novel business model that's being used to take advantage of the flexibility of distributed storage. How soon is storage really a mainstream capacity option? Well, Excel's looking at this, and they're following the cost range in which batteries are potentially compete with peaking plants. That's that blue bar at the bottom. And their projections are it's either happening now or by 2022. And I think that that's instructive, right, is that this is something that folks are looking at as actually not just a far-off future, but happening on the horizon or now. So that's one key change. And here's some examples of batteries providing that capacity sort of function, some that are operating, a lot that are in development right now. There's a lot of battery that's in development. As a part of infrastructure, I think the key thing to understand here is that it's not just about increasing the lifetime of these assets by allowing you to avoid more expensive, much more difficult upgrades, but also the fact that you have a more resilient infrastructure. The hosting capacity piece of this is particularly important on the distribution system in places where folks are trying to put more distributed energy resources to be able to manage the impacts on that grid. EV charging being, I think, a perfect example of where folks are now putting batteries into the grid where DC fast charging is, so that when you add a DC fast charging vehicle to the grid, your distribution circuit doesn't get overloaded. This kind of, again, efficiency and ability to use your system flexibly is going to be really important. And that's going to be increasingly important as more and more parts of the economy electrify, transportation being the one that I think most people are thinking about, but industrial processes, perhaps more heating. For folks who are in water-stressed environments, you might see more desalination. There's going to be a lot more electricity used, and it's going to be used in different profiles. And we see this as being a key way to integrate new different kinds of demand that may be showing up in, again, harder to manage ways. Note that also that bottom picture is a containerized battery on wheels. It's not an electric vehicle, it's a trailerized battery that can plug into a substation, which Con Ed is piloting right now to bring from substation to substation for seasonal needs. So this is also an asset that doesn't strand very easily. You can generally, if it's containerized, pick it up and move it. Another thing to be watching, this is an economics crowd, I haven't been talking much about economics, is rate design. And understanding that for folks who are looking at this from a customer-sided standpoint, the rate signals folks are facing may have an impact on how much this gets deployed as a customer-sided asset. Demand charges being the thing that has traditionally spurred this. As I noted, storage can really go with anything, and we're seeing it go with anything. And the key thing to bear in mind here is there's no real reason from a grid operation standpoint necessarily that you have to put storage with a specific asset. If you have a grid that doesn't have transmission constraints within it, you can operate these assets in coordination. You might put them together for permitting and interconnection efficiencies, or because the tax regimen advantages it, but really this goes with just about anything. And then finally, from a standpoint of the clean energy side, which I know a lot of folks are interested in, we see storage primarily helping with avoiding curtailment in the belly of the duct, for example, and helping with the flexible capacity needed to deal with these very, very quick changes in net load profiles. I want to pull out just a utility in New Mexico, PNM, who's looking at how their system is changing as they go to higher and higher renewables, and the value of flexibility is going to increase as your renewables increase. What they're looking at is not just your traditional loss of load expectation, but also looking at not just the peak demand, but the interval of greatest change in net load, that instantaneous swing that might be in a large ramp with a system with much more renewables in it. And when they look at those two things together, they're finding that in that future, a battery is going to make more economic sense and more reliability sense than a similarly situated gas turbine. So that's something to bear in mind here. This is just a quick review. This is certainly for folks who are involved in the conversation about clean energy, and I know Eric will have far more nuance to add to this conversation. This is the way that we see it being a part of that conversation. And the one thing that I want to sort of turn now from applications to a very quick understanding of the policy standpoint, which I think about is one of our major, don't worry, I'm going to finish before your 2 minutes. So, one of the key things here to bear in mind is that not all of the benefits of storage are actually necessarily monetizable. In fact, Massachusetts in their 2016 State of Charge report, which I highly recommend, it's really the first state to study energy storage deployment with a really high degree of fidelity, not just a cost-benefit analysis, but also really thinking about what are the different values this provides in the system. And what the findings there were, which I think is really instructive, is that, and remember, they're in a restructured market, right, in the ISM New England system, that the non-monetized system benefits of these storage deployments are greater than 2 times the actually accessible revenues of those storage facilities in the market. So there's a lot of value to the system that cannot accrue to the battery, and in this environment, that means maybe those projects don't get built. So a lot of what we're thinking about is this question of value and recognizing that if the benefits justify the costs, but the way in which they accrue doesn't show up to the project developer, that is seems like a challenge that policy might be able to deal with. And I know, just back to my original point on system capacity and network capacity, this study found that just reducing system peaks and local peaks was more than 50% of the benefits of these deployments. So when we think about this at ESA in terms of the hurdles to energy storage deployment, they generally fall into 3 categories. One is this ability to actually value and compensate energy storage for the flexibility it provides. Those price signals might not exist, and that means folks are looking at rate design, if it's in a customer standpoint, utility programs and permits, and specifically also wholesale market design, market products for those who are in RTO environments. Secondarily, the inability to compete in grid planning and procurement. This has been changing, I think, more rapidly than most places, but really that means having storage actually as an appropriately considered resource in integrated resource planning and distribution planning, having wholesale market rules that actually allow it to compete. And then the third is access to the grid. Literally physically accessing the grid is still a significant barrier for storage because it does not look like a generator, it does not look like a load, it looks kind of like both and neither. And so interconnection processes really do need to be updated, as well as understanding that storage, as I mentioned previously, can provide multiple services. It can provide an end-user service while providing grid services. It can provide transmission while providing generation. The importance of that is that those multiple uses are what drive a lot of the efficiency, but regulatory frameworks may not allow it at this time. I'm sure we'll have a lot more to talk about in the discussion ahead. So thank you.
Thanks, Jason.
So I should start with a little disclaimer. You guys might know me as the guy with the hat. I thought I'd be a little more professional today, but I've been getting grief from everybody about this. So this is me, I'm Eric Hayden. I spend a lot of my time thinking about how energy storage fits into the electricity system, so I'm going to share some of those ideas and thoughts. I'm hopefully going to say some things. I tried to make this content that maybe is new or surprising, things you haven't heard before, but it's all centered around this theme: does the grid really need energy storage? So the first place I'd like to stop is the Holy Grail narrative. If you've read about energy storage, you've probably heard the Holy Grail narrative. And the narrative probably sounds something like this: we like wind and solar, but they're renewable, but they're intermittent, right? They come and go, and we need energy storage on the grid to unlock and unleash the full potential of renewables. You see this all over the place in the storage literature. I don't like this analogy that much. I think it actually obscures more than it reveals about the nature and need for energy storage. And part of the reason is that it kind of ignores all of the many other things that storage can do for us, in addition to or on top of integrating renewables. So if we're thinking about renewables and the need for energy storage, first place to stop might be market prices. And we put on a decent amount of wind and solar onto electricity grids in the last 10 years or so. So what do electricity markets say? So we could stop at capacity markets maybe and say, okay, if we need help meeting peak demand, then we should probably see capacity prices going up. But a lot of the US capacity prices have been, they're always noisy, but they're pretty flat. In some places, they've kind of dropped scandalously low in recent years, suggesting we don't need that much aid with managing peak. If wind and solar are causing all sorts of short-term variability, second-to-second balancing problems, you might expect to see that in terms of frequency regulation prices going up. But across the US, frequency regulation prices tend to be a lot lower than what they were 10 years ago. I'm not cherry-picking data. I have to pick one place to show, but this is New York. And a third place you might look is in the variability of electricity prices. So if wind and solar are driving all sorts of electricity price fluctuations, and we want storage to smooth things out, then you'd expect to see that in measures of variability of electricity prices. But that also, in a lot of the US, is actually declining over the past 10 years. There is one exception, one important exception, of course, and that is the canary in the coal mine for renewables integration, California. So in California, so here's the last 5 years of electricity prices. You can see a little bit of an increase in the electricity price variability there. So at least this is better news for storage. But it's not amazing. Overall, market signals don't seem to be indicating, like, yeah, let's add a whole bunch of storage. We absolutely need it. Thank goodness it's shown up on time. And why is that? So I have a pretty short answer to that question that a lot of people haven't maybe thought of, and that is natural gas. Natural gas is a great competitor for energy storage, unfortunately for the storage industry. It ramps quickly, provides peaking capacity, plays well with renewables, all these great things. And so it makes it harder for energy storage to compete in these markets. So this is some work we did looking at how much money a storage device could make from energy arbitrage. That's the sort of buy low, sell high thing. In Washington, D.C., actual electricity prices, and said, hey, how does this compare to whatever the natural gas price happened to be that month? There's a pretty strong correlation. Here's the same data in a scatter plot. The correlations may be even clearer. Natural gas price drives this revenue stream for storage. And we didn't cherry pick DC. Here's Chicago, similar trend, New York City. We did this for Texas, California, and we see similar trends. And it's also not just energy arbitrage. There's other services that have similar relationships, like frequency regulation. Since natural gas provides a lot of this service, when the gas price goes up, the frequency regulation prices go up, and that drives how much money storage could make doing this service. So maybe you don't like natural gas. Maybe you think the prices will go up. And in fact, I would say if I were in the storage industry, while everyone pays attention to renewables and storage, right, that's the common narrative, I actually think you should pay more attention to natural gas price. So a moderate increase in natural gas price, 40 or 50%, would probably do more for storage economics than if we doubled the amount of wind and solar on the grid. But natural gas isn't the only game in town. There's other competitors for energy storage. One of them is demand response, right? This is up and coming, a lot of interest, a lot of investment, just like energy storage. There's a lot of new market rules that are allowing you to compete more directly with traditional assets. A second option is new transmission. So in West Texas, they used to have a problem where they put in so much wind, it was getting curtailed, there were negative prices. Energy storage folks were very excited about this. And then Texas went and solved the problem by building a whole bunch of new transmission to bring that wind power to the eastern half of the state where the load centers are. A related thing is balancing area consolidation. So California is working with the neighboring system operators to try and expand the balancing area to help them balance out their excess supply and demand with the region as a whole. And an often overlooked option is just straight up curtailment. So in my life, sometimes I do things that waste water, right? Sorry. But I never waste a good scotch, right? A good scotch, I don't waste any of that. But if scotch was the same price as water, well, I'd probably drink more scotch. But I'd also probably waste a lot more scotch as well. And the same thing is true for solar power, right? It used to be the case it was expensive. We wanted to make great use of every kilowatt hour. But solar is getting amazingly inexpensive on the kilowatt hour basis. So maybe a solution that competes with storage is just build a lot of solar and let it spill all over the place. That's an opportunity for storage, of course, but it's also, in a sense, a competition for storage. So, does the grid really need energy storage? I'm not going to quite answer this yet, but you probably see where I'm headed. I'm going to ask more questions. Do bicycles need multiple gears and derailleurs? Like, couldn't we just have fixed-speed bicycles? It's not really my cup of tea, but there's probably like hipsters that think so. Does Italian food really need tomatoes? Right? The tomato is a New World vegetable. It's hard to believe, but Italians went for thousands of years without a single tomato. It's only the last couple of hundred years they've had it. But it's hard to imagine modern Italian cuisine without the tomato, right? And I think this is what will be said of the grid and energy storage 20 or 30 years from now. So we don't need energy storage. What might we want it for? I think a first thing is getting rid of peaker plants. Peaker plants were never that good of an idea anyway. It was our best solution, but it wasn't that great of a solution. The idea going in for a peaker plant, right, is I'm going to build this big capital asset and I'm not going to use it. Well, I'll use it maybe 50 hours a year. Maybe 0 hours a year, right? That's not a very good use of capital. It would be great if we had an alternative, and storage is coming to help us with that. So this is a figure from the University of Minnesota. They did a storage workshop. They said, yeah, peaker plants are a cheaper option today, but within 5 years, we think storage will be a cheaper option for Minnesota. It's even better if you couple it with solar. Although, importantly, they noted that's entirely due to the tax incentives that you get if you put it with solar. It wasn't anything special about that. Green Tech Media did a similar but broader study looking at all of the peaker plants in the US, and they came to the conclusion that within 10 years, about 2/3 of peaker plants will be under threat, just competitively, from energy storage. So that's a huge potential market for storage. So does this mean that traditional generators are on the way out and it's just storage from here on out? I would say not to worry about that quite happening yet. And the reason is because traditional generators and storage are very different beasts with a very different set of capabilities and limitations. So if somebody asks you who would win in a fight between a bear and a shark, hopefully your first question is, what's the environment? Is this in the ocean? Are they fighting in the forest? Context matters because they're so very different beasts. And this is true for traditional generators and storage. If we're looking at things like meeting an annual peak a handful of hours out of the year, That's tough to do with a traditional generator, or at least expensive to do, but that's the easiest thing you can do with storage. That's great. You love to do that, you don't need much capacity, and you're going to use your storage every other day out of the year for energy arbitrage and spinning reserve and things like this. You get to the point where you're going to talk about mid-cycling. I want to run something that's there 4 hours a day for a whole bunch of days in the year. That's easier, or cheaper at least, to do with a traditional generator, but it's actually more expensive to provide that service with energy storage because you need more capacity and you need to keep more of it in reserve and not do those other services. And when you get to kind of longer term fill-in, you know, what happens if the wind drops off for weeks? You know, what happens if we have high demand in New England for a week at a time? Well, generators love to run for a week at a time, as long as you're paying them. And but for storage, you know, that's just not in the near term. Maybe in a couple decades we'll talk about that. But this contest, this is actually a feature and not a bug. In short, storage is good at the things that traditional generators don't like to do, and that's great for us. A second question is about where storage should be placed. So Jason brought this up, so I'll cruise through it a little faster. Everybody thinks about storage and renewables, and yes, as we add more wind and solar, which is coming and coming quickly, that's going to improve the economics for storage, but that doesn't necessarily mean the storage needs to go with the wind and solar. There's a few good reasons for that. The biggest one right now, when you read about solar plus storage projects, is that you get a pretty good tax incentive on the storage portion of your solar plus storage plant. That's driving a lot of the adoption. There's a few other more physical, non-policy related reasons as well. But if you study storage like I do, and you think about a storage plus whatever plant, coal, solar, you pretty quickly realize that the optimal way to operate the joint plant is to figure out the separate optimal operation of both of the two halves and do that. And if you're going to operate them independently, you know, why not site them independently? And if you're siting them independently, where would I put storage? One of the things that I'm excited about is distributed storage. So this figure here, so distributed storage implying that you're putting it like at substations or at customers or maybe even behind the meter, customer-owned storage. So this figure here is from a Brattle study about Texas that came to two interesting conclusions. Number one, within a couple of years, Texas could cost-effectively put in several gigawatts of energy storage. It's a lot. And number two, that they recommended distributed energy storage as being a better option. Even though it costs more, right? Economies of scale would say put it centralized, but the benefits of putting it out of the distribution system actually outweigh those additional costs. In short, while distributed storage has worse economics on average, we don't want to build the average project. We want to build the most valuable project. And there's a higher distribution, so the most valuable projects on the distribution side are more valuable. There's a big challenge here, at least for behind-the-meter storage, and that is rate design. So when electric utilities have been designing rates, they didn't think about storage. Of course not, it didn't really exist until recently. And so some of the rates motivate bad behavior from storage owners. People can make money doing things that are actually bad for the grid. And some of the rates don't motivate good behavior. There's something that an owner could do with storage that would be beneficial, but it actually isn't paid for. And so what we want to do is revise some of these rates so that the owner can get value out of their storage, and so that the grid as a whole also gets value out of the storage, right? So we don't have any perverse incentives. I want to talk about the cost of storage. So if you've ever been to an energy storage conference, here's a thing that we like to do, is the presenter says, storage can provide many services. And then the audience says, amen. And it's like we always say it, and I sort of roll my eyes each time because it turns out like other things provide many services, right? A gas turbine provides energy and capacity and spinning reserve and frequency regulation. The place where I think this is important is when you look at the breadth of possible applications and different markets that storage will go into now and into the future. It's much wider than for traditional assets, and I've sort of drawn my cartoon here, so don't necessarily assume this is the correct demand curve for storage. But storage is expensive today, and it can't compete in most of these applications, not even close. But storage is being adopted quickly, mostly driven by electric cars now, but potentially driven by grid applications in the future, and the price is coming down. So the game isn't to compete in everything today. The game is to compete in certain markets today, build out those markets, and then through a process of sort of cascading diffusion, bring down the prices, economies of scale and whatnot, so that it can compete in further markets in the future. Now, I don't know if storage will be able to follow this quick trajectory, price declines. But if you've looked at the recent history, I wouldn't bet a lot of money against storage price declines. So my last question is, what's the future of energy storage? Where is energy storage going? I think there's interesting and competing visions on this. So to sort of unfairly construe one extreme, you have like Tesla on one side. And so like Tesla's vision to some degree seems to be like shiny, fancy devices, luxury items. You put them here so your neighbors see. They're probably connected to your rooftop. You probably have an app on your phone. You're thinking about how much storage you have. I'm not a big fan, actually, of this vision of storage. This is my ideal vision of the future of energy storage. I want to see a future of energy storage where it's boring, where it's invisible, where it's really cheap, and it's sort of all over the place. So that's my ideal vision. And so to come back to my big question, does the grid really need energy storage? My answer is no, we don't need energy storage, but we probably actually want a lot of it just for economic reasons and to help us achieve some of our other goals. Thank you.
As Ben said, I'm in the Maryland House of Delegates, the Maryland State Legislature, so I'm happy to be with all of you. I'm less happy to be in Virginia. Next year. Those were really great informative presentations from Jason, who I've worked with a lot, and Eric. Now it's on to the political hackery, unfortunately. And the truth is that's actually really important because a lot of the things they describe require a political process to get there. So obviously as a politician, I aspire to be like the guy on my right. In reality, I'm more like Vice President Stephen Meyer on my left. But you got to deal with guys like us. That's just the reality of our system. We're still a democracy, although I haven't checked Twitter since I've been up here. So I thought, I'm going to offer basically a state perspective. Obviously, there's a lot of important action at the federal level that many of you have probably worked on. There have been proposals for an energy storage at the national level. There's a lot of things with tax policy at the national level that are really important. I'm going to talk more about the states. That's my area of interest and somewhat expertise. And so I'm just going through some of who I view as some of the state leaders. And there's a lot of states doing this work. I don't mean to exclude anybody, but these are some of the real leaders on this. And I think to a lot of you, this is probably pretty familiar. California, of course, Jason can correct me with anything I miss, but California, sorry to say it, but they're the holy grail of storage, right? I mean, they really have done a lot. Starting in 2013, they really jump-started the regulatory process by passing legislation requiring their PUC to have their investor-owned utilities purchase a certain amount of energy storage. And even before that mandate was fully in effect, they added to it with another piece of legislation in 2016 to sort of create an additional specialized procurement requirement for their utilities behind-the-meter storage. And so this has been a model for other states. I've tried to make it a model for Maryland, but it's been a model for some of the other states that I'll talk about, but it's been pretty significant in really jump-starting a lot of interest in storage. And one report I looked at found that 74% of the behind-the-meter storage that's been deployed is in just 2 states, California and Hawaii. And I think that's not too surprising, but part of that, especially in California, is really policy-driven. That's been something that the state has taken an interest, the PUC has sort of ordered it, and so it's coming online in a quick way. Oregon is another great leader. They followed the California model. Their legislation, which passed in 2015, basically said there's going to be a minimum amount of storage that the utilities have to procure, storage capacity, and then the PUC can study whether or not that amount should go higher. So there's a minimum in there, and then it can go higher. And if you think about it, that's sort of one of the options, right? The policymakers can say, we want there to be a storage mandate, and a minimum has to be this amount. Another approach, which is what Nevada did, so I'll just jump ahead, is their bill, as I understand it, was the PSC or the PUC can study whether or not there should be a storage mandate, but there isn't a minimum requirement. So they're sort of a step back, right? They have the threshold question of should we even do this before they put in, yes, we're going to do this, and you can go higher than the amount specified. Massachusetts, obviously a real leader. Jason talked about the study they did, and they now have their own mandate requirement on utilities as a result of 2016 legislation. I think theirs is 200 megawatt hours by 2020. Hawaii is interesting because they don't have the same policy-driven mandates. They had an attempt at a tax credit, which did not go through. Their storage leadership has been more market-driven. It's been more of an effect of their very large RPS, the Renewable Portfolio Standard, and I think just the structure of their grid being so disconnected. And so they've been sort of more of a natural leader with less political hacks driving the process. New Jersey has been a leader in this. They passed a pretty significant bill that's going to have by 2021 a mandate of 600 megawatts with a 2,000 megawatt goal by 2030. So pretty big numbers. I mean, if you compare that to California's numbers, that's bigger than what California's current mandate is. New York, similarly, going big. Theirs is more of a gubernatorial-driven process than a particular statute that's passed. Their goal right now, I believe, is 1,500 megawatts by 2025. I'll skip over Nevada since I mentioned them, and then of course the most important state up here, Maryland. Maryland is the first state in the country to have a tax credit specifically targeted for energy storage devices. It has a cap, so there's only $750,000 a year available, and there's a cap on each applicant to 30% of the cost of the system. And then that 30% can't exceed $5,000 for residential or $75,000 for commercial. I'll talk in a few minutes about how the subscription to that has been, how it's been used since it passed 2 years ago. And again, other states are acting. You saw on Jason's slides, Arizona, Colorado. Lots of states are doing things, but those are some of the ones that have really led the way, and I think show some of the options. And I'll just say about Maryland, in addition to the tax credit, which is what gets Maryland on the list, there's also been some other efforts. Our PSC, our Public Service Commission, has been undergoing basically a study process to figure out what the regulatory constraints are on energy storage, what needs to be done to sort of ease the way there to allow for more energy storage. And then we've also passed legislation to have something called the Power Plant Research Program, which is part of our executive branch government, study basically incentives for storage and whether other incentives besides the tax credit make sense for Maryland. But the tax credit is Maryland's real claim to fame in the storage universe, because that's actually currently being used. So options for states, again, I went through a lot of these just now. Procurement targets, I'd say, are the really big one. Tax credits, Maryland's has passed. Hawaii has tried it. A few other states have tried it. I think you'll see more of that, especially as a state legislator. I can tell you the best way to pass a bill is to say, but X state is doing it. And so once Maryland has some success, I think other states will look at it and say, yeah, that's another thing we can do. Pairing storage with the Renewable Portfolio Standard is really important. I understand that storage has much broader applications than just being paired with renewables, but for at least Democratic politicians, that obviously has a lot of appeal. So figuring out how it fits in with the RPS is really important. There's an indirect way, sort of gets you down there, in that as you increase your amount of renewables, you need storage to help deal with things like the evening hours when we all turn on our lights and turn on our microwaves and dishwashers and washing machines. But you could also do more direct things. You could do a double credit for a renewable energy credit, for example, rec multiplication. Again, pilot projects are a big one. When I first got to Annapolis, I spoke to some folks about whether it made sense to try to do some pilot projects in Maryland. Was that something that we could do through legislation? And what one expert said to me was, hey, look, we know how to plug a battery into the grid. I think he was oversimplifying. I think pilot projects can have a lot of advantages. I think there's a lot of nuances to unfold, even if the basic technology is understood. For example, when you tell someone it's a great idea to have, or a nice idea to have one of those power walls paired with their solar, and then you tell them that the utility can reach in and pull out electricity from there when they need it, all of a sudden the conversation changes. So even that customer expectation idea is something that I think needs further exploration. We've seen it with smart meters at the local policy level that people get very uncomfortable. I think you can see a similar thing with behind-the-meter consumer batteries. So I do think there are some things to pilot. As a state legislator, I have to deal with a lot of the stakeholders who work on these things. I'll just run through these quickly. But the biggest one is ratepayers and advocates for ratepayers. They really need to understand, what are the costs, what are the benefits, how is it going to affect their bottom line. Obviously that's a big part of any regulatory proceeding. It's also a huge part of any political process. So any piece of legislation that's going to go forward, obviously thinking about the ratepayers is going to be a big part of the conversation. In my state, for me, the environmental community is a part of that conversation. Again, a lot of the opportunities with storage are not really linked to our sort of clean energy future that a lot of us have in mind. Does that matter? Do we need to change what the policy looks like to target it more closely to just the renewable pairing context, or is it okay that it has all these other sort of arbitrage opportunities that may not be what environmentalists have in mind? I know this is about batteries, but what about pumped hydro, right, which is our sort of biggest currently existing source of energy storage? A lot of people in the environmental community are not huge fans of that kind of project, so that's a major stakeholder. Obviously, the utilities, Maryland is a deregulated state, so the utilities are also the distributors. Of course, there's also generation to keep in mind, and then the third-party storage owners. And so there's a lot of nuance to work with there. The big one we found in Maryland is, as a deregulated state, the utilities, the distributors, do not have the ability to own generation assets, which storage can often be. And so figuring out that nuance is pretty significant. Regulators and the administration are obviously a very significant stakeholder as well. And those are separate things, right? I mean, even though PSCs and PUCs are typically appointed by the governor, they're quasi-independent. Then there's also the administrative agencies. In Maryland, we have the Maryland Energy Administration, for example, that's very interested in this, which is separate from the Public Service Commission. So working through all those stakeholders can be pretty complicated. So I'll just really quickly talk about my own experience in Maryland. As I said, I'm a political hack, so why did I get interested in energy storage? I needed a different way to talk about the environment and clean energy, and saw what they were doing in California, so started learning more about it. I didn't have a ton of knowledge when I went in, learned a lot, and then had to try to relay that knowledge to my colleagues. When I first went to the Economic Matters Committee, that has jurisdiction over this, it was like speaking Greek. They had no idea what I was talking about, right? This was, the legislative session ended in mid-April of 2015. We adjourned. 2 weeks later, the Tesla Powerwall was announced, right? This was like the Rosetta Stone for energy storage discussions in Maryland, because all of a sudden my legislative colleague said to me, oh, that's what you were talking about. And I can't believe I couldn't explain as well as Elon Musk. I mean, I'm really sort of offended by that. But that really helped. It really jump-started conversations. We went back in 2016. And Jason came and had a lot of stakeholder meetings. We had a really good hearing. We actually had some positive progress on the bill. Didn't quite get it through, but positioned us nicely to come back in 2017 and get through what ended up being the study bill, study incentives, as well as that tax credit bill, which I was not the sponsor of. But a lot of the education that Jason and I and others provided helped to bring about the tax credit bill. We also, at the same time, had that regulatory proceeding I mentioned earlier as well. That's unfolding. And so we hope that all these things will coalesce to come back in 2019 or maybe 2020 and do more on the policy front. But what we've already done, even, I think, has helped move the ball forward in Maryland. Obviously, there's a lot of choke points when you're doing public policy. All those stakeholders can be a choke point. The need for education, because this stuff is pretty complex. I mean, I've been working on this for 5 years now, and I learned a lot just sitting watching those quick presentations. Then there's just a capacity issue. Most state legislatures in the country, 40 of them, are part-time. We meet for 90 days in the Maryland General Assembly, and so getting through complex issues in 90 days is a pretty difficult thing to do. In fact, most of the states where they've had great success, Massachusetts, New York, California, they have legislatures that meet for much longer periods of time in California, so that's actually an issue. Money's an issue. Money to the effect on the ratepayers, obviously, which I talked a lot about, but also the cost of even doing these studies is an issue. The bill I wrote 2 years ago was a very expansive, exciting study. At the last minute, the agency that was going to do it said, we don't have the budget for this. You got to pare this thing back, or we're going to strongly encourage the bill not to pass. And so we did that. We had to pare it back to pay for the bill. And of course, the tax credit has a cost also, and so that's why it's capped at $750,000. At $750,000 a year. I'll just briefly talk about some of the success with that tax credit, what it's been used for, in case some of you are going to go try to replicate it. So it's 30 applications have been approved thus far, about $100,000 in tax credits on a total investment of $360,000, and 23 of the credits have been for Tesla Powerwalls. All of the credits have been for the residential side so far, nothing on the commercial side. So it's mostly been Tesla Powerwalls and a handful of other similar products. I would just leave you with this note. I know we all hate politics and roll our eyes a bit at the government, but state legislatures are nothing like Washington. They're very accessible. Things actually happen. So I would just encourage you, wherever you're from, to go engage if you're interested in these issues or whatever energy issue you're interested in, and go lend your expertise and go push them to do things. Because a lot can happen at the state level that can really have a big impact, and I hope you'll be a part of that. I was going to say positive charge, but I'll say positive change. Thanks very much for being here.
So these are all 20 on a scale of 10. Thank you. I want to basically sit down, so I want to par with my panelists, if I can presume to do that. So there are a couple of questions I just want to raise, and we'll open it up after that. I'm intrigued by kind of a thread through each of the talks about the benefits of battery, in particular battery storage, that we have difficulty quantifying. I think Jason referred to non-monetized benefits. Eric and Jason both referred to flexibility, and Mark echoed this as well. And so I'm going to ask this question in the context of Los Angeles, where it's well known that there's a tremendous amount of solar. I think Jason showed the duck curve, which is more interesting in terms of the ramp up that's required. No, we can't just build more solar to compensate for the lack of storage, because it shuts off faithfully every night, right in the middle of the evening peak. So, in many times of the year. So it's this ramp up of generation. I imagine the sound of 1,000 lawnmowers, starting up as the sun starts to go down. The more solar you've got, which is, I guess, a good thing, believed to be a good thing in LA, a place with a lot of sun, then you need a lot of gas. So one of our clients is Los Angeles Department of Water and Power. We were working with them right in the middle of the sudden announcement that Aliso Canyon failed. And the question is, how do I get this gas to all the power plants this fast? This much gas, this fast? And the answer, of course, is storage, gas storage. Keeping the system powered through pipelines and gas storage. Well, with the failure of Aliso Canyon, you can imagine the gray hairs that sprout and the demand for storage. How do you integrate? There's just no way you could use a pipeline. As more and more solar is on. Speaking as someone's looked at gas pipelines as a day job for many years, decades, you really cannot, I think, ultimately depend on the system to provide the gas grid, to provide that much jump in generation fast. So, on comes storage. It's not being measured against that. I don't know if there's a way, maybe, and it's to Eric as well. How do we think of an analytic framework that will allow us to measure the benefit of storage against this increasingly real, phenomenon? In fact, maybe it's liquids. Liquefied. We did an LNG storage project in Maine. We worked on it. It didn't get built. But we're talking about it costs about $25 a million BTU. So when I look at the cost of gas against storage, maybe it isn't gas. Maybe we're looking at the wrong thing when we're thinking about the ramp up. Maybe it's oil. It's distillate fuel.
Not in LA.
Not in LA. So, or not in my neighborhood, So it's got to be something clean. And even a gas-fired power plant or LNG-fired mini plant in neighborhoods is to be objectionable, as it was in Maine.
Well, education is really important here because there are people that wanted to shut down the entire gas storage facility in California.
Yes. Let me let.
Sure. And this concept of value, and what I hear you say is two things. So the way I would frame this is that flexibility that storage provides is a part of reliability, which is perhaps some amount of uncertainty, but it is predictable uncertainty. It is uncertainty you can quantify. So like the evening ramp being one of those. You know it's going to happen every day. You might not know the exact level of the ramp, the exact time, but you have some idea that what it's going to look like. And one of the questions there is, how do you value that flexibility? In California, ISO, for example, there's this concept of flexible landing as a actual monetizable service. I think that it's really being worked out how well that works. But the concept here, this idea that you have some sort of flexible capacity that can provide that very, very precise ramp, because one of the issues here, right, is that a mechanical generator kind of overshoots what it needs to provide, then it undershoots what it needs to provide because it's using a mechanical governor to effectively change the output of the system, and it can't just respond totally instantaneously. That's one of the benefits of batteries, the high precision. And so there's this idea of like maybe you have some sort of market product or service that monetizes that ramping capability to California. So is doing that. MISO has something sort of in the works. Other folks are looking at multi-period look-aheads and optimizations. There's a question as to whether better energy price formation could provide that signal. The other side of this is the way flexibility provides resilience value. And this would be like Aliso Canyon shutting offline unexpectedly. That is Knightian uncertainty, stuff that you can't predict, at least not very well. There's some risk though, and you can try to manage that risk. And I think that the key thing to understand here with storage is that it provides significant resilience value because of its quick ability to deploy, its relative lack of environmental requirements and footprint. It's part of why you're seeing it deployed in post-disaster environments increasingly, like in Puerto Rico. And I think that that is something we haven't figured out how to value or monetize effectively. We don't do very good with tail risks. It would be more of an actuarial type approach, I would think.
Decision, some kind of a decision.
But some sort of way in which that is a part of it. And in fact, all these discussions at the federal level about resilience and like maybe we need to, have some sort of plan for different generators for their different attributes. Take away the politics of good or bad, what's being proposed by the administration or others. At the end of the day, there is this question of, is this something that we can actually wrap a cost benefit around in some way? Because I don't think that we have a good answer for that. But certainly, battery storage in Aliso Canyon has proven exactly that it does provide that value.
Yeah, so I actually have 3 things in response to your question. So you said you can't do it with solar, right? You can't just add more solar and meet your peak demand. But you'd be surprised at how much you can get away with if you built more solar panels and just pointed them west. You can actually fill in a decent amount of that peaking demand. If solar gets cheap enough, that's an alternative to south-facing solar plus storage. It'll come in competition. But a second point is that to some degree, a properly functioning energy market already values flexibility. So if you look at the solar duck curve, the price goes really low at noon and gets really high at 5 p.m. right, and it ramps up. It basically rewards generators that can ramp really quickly. If you're a type of generator that can turn off during the low price in the middle of the day and easily ramp back up, you can capture that value. And if you're the type of generator that has to run flat out, you're presumably maybe losing money in the middle of the day. So energy markets, if they're well designed, already penalize inflexible resources and provide benefits to flexible resources in as much as that's needed on the system. I think there's a lot to be said that California's electricity market isn't completely free-flowing. It's not completely economic. There are some outside interventions that are interfering with the prices. But as an economically minded person, my view is that the solution to that is to try and fix the market price formation rather than say, well, the market prices are all goofed up, so let's demand that we put in storage. And then the third point I would make, about the unaccounted for benefits of storage. I'm the bad cop, I guess, here today. But the one thing that is true, a lot of generators have value that are produced that they're not paid for. So existing generators also produce value they're not compensated for. And so some of the uncompensated for benefits, in some of the studies that have been done, are what economists would probably refer to as consumer surplus. And you wouldn't necessarily be compensated for that even if you were a traditional generator. I still think there's arguments to be made that storage is not completely compensated for all of its market benefits. But to me, the solution is more, let's try and fix the markets rather than just pushing in storage into the market, even though I'm sure politically it's a lot easier to get incentives and mandates than to fix the markets.
It sounded like a challenge.
Yeah, I mean, you just hit on it. I mean, markets are great, and looking at the pricing is great, but guys like me love to throw externalities at the market, right? So part of the reason California has these issues is because they have these really aggressive targets. So I'll just give you the context for Maryland, just because that's obviously the one I know the best. Right now, Maryland has a 25% by 2020 renewables goal. But so far, we're only at 5 to 7% of wind and solar at the current time, and of course, the RPS is much broader than wind.